Yeah, no.
Yeah, we're fine. There's just not going in there. Nope, I got it. Are we not showing on the screen? No.
We'll log in. With that screen saver, maybe.
So, the HDMI became unplugged. I don't know how that happened. Okay, there we go. All right, I tested the microphone. So you'll just need to turn it on, and then I'm sorry, we don't have a lapel mic with batteries. And then this should work. The slide.
Joe Ray
the
thought so
clicker.
I come to Roy. And I list a lot of audio feedback using a microphone in a room with speakers. This is just a sound test. How we doing up there? Oh, good, perfect.
All right, good deal.
Man, now I gotta have a laser and this is gonna be tough.
Do you
Yes,
have
hello.
the pointer? Okay.
So these are the move forward we've had, and then this one is.
You got it. I am a veteran of 10,000.
And if you need water, I know you got coffee, and if you do need, like, I always get parched when I'm talking.
Which one was my water bottle? This?
It's this one, yeah.
Okay.
Oh, let me hide these two while I'm at it.
I was sharing the screen,
Yeah.
and if you walk on the other side, nobody's. Is that?
Right, so I'm gonna use this as a little wall that will stop me.
Yeah, so yeah, if you don't go past this black bar into the wall, you should be in the picture.
What do you call it? Black bar? That?
Yeah, there. On the wall.
Oh, this.
Yeah.
Okay, right, so.
That's mounted. So then here's the camera and it will follow you on the side. If you go into the other section, it's fine, but you'll just be a disadvantage.
Okay, this is my barricade to prevent
Okay.
me. I tend to sort of use the space like a Baptist preacher when I do this. So I'm gonna be mobile. Yeah. What do you?
Bring a QR code, so please make sure you sign in today.
Did I write that?
Yeah, I think so.
Okay, all right, I shouldn't compliment it.
Good job.
I was doing it, we were on a call, looking at paper and like looking at revisions. And one of the sentences was highlighted because it was one of the. And I was like, that's a really good sentence, like, and the guy was like, dude, you wrote that. I thought I was complimenting. I was so sorry.
Happens.
Happens all the time.
Um,
How well attended are these? All of the grad
all
students?
grad students, yeah.
Wow, okay.
And yeah, some of them are in person, but others are not, so.
Tomorrow, I don't know what your schedule is, but if there's any reason.
Yeah, I've got some sun, but afterwards,
Yeah, I'll probably head back during lunch.
yeah, we can, some plans.
I'll have to steal this from you when you're done, because I hang these on my bulletin board up on my desk, so that people know I do.
Contributed to.
Yeah, that I do stuff.
Should nobody questions that.
Well, it's actually my way of proving to people that I do the real job and not just outreach, because the outreach is highly visible. This stuff is much less visible, so I make sure that people want.
Yeah, well, that's relative way to the other issue very important.
It is very important, but it's important that people know that you're not just, Carl Sagan was denied tenure, you know this? Carl Sagan did not get tenure because they said he was doing too much Carl Sagan stuff and not enough actual science, and so he, I believe, Cornell. And they said, oh, your research is too derivative and not enough. Much. Cornell's lost, right?
Have you seen any like, people applying to your program after seeing your videos or things like that?
No, I don't think that.
Because you don't track it, but probably.
Yeah, maybe. So I try to like do calls with high schools where like we graduate so many high school teachers that it's like, hey, let's do an Ask a Physicist day. And they can watch a few videos and then like I can show up, I could wear a Kurtz Gazette t-shirt and they can ask me questions about it, and I can pinch them on coming to college to be a physics major. So that's been my way of just being like, hello, it's me from Kurtz Gazette. Don't you want to come be a physicist?
I'm also.
Yeah, also fantastic.
I completely agree with social media management to one of my students just because I just
Active social media management.
no group social media. I guess we don't have a presence.
Don't you know that blue sky is the most important place on the internet? Obviously,
Me not knowing exactly what that means. That's exactly.
Is she smiling because she's hip and with it? And she knows,
Just learned about this yesterday.
but that means you're hip and with it because she knows about it.
So we'll see. We'll see.
There are a lot of academics who have spent a decade building a Twitter following
And now.
that are crying and just like they're distraught that this thing that they built, it doesn't matter anymore. Twitter is just like.
Yeah, no, I didn't encourage this to create our channel.
This was the advice that they gave to me as a grad student, like, you sit in a room because you should really have a social media presence, and
Yeah,
will make you visible. What trash is this? No, nothing important. In the off chance that someone might give me a job someday, I need to keep up with.
I don't know. I've heard this type of advice, but
Never give anyone that.
I think it depends. You, of course, are very well versed in that. I have other friends who are creation artists. Me, yes, I don't exist. I exist in real life. I come to my own.
I also prefer to exist in real life, like, and writing for media is great. I mean, that's a real life thing that I do, but I don't have to keep up with. It's because it doesn't matter. It's like being a socialite. You have to be seen at all these parties and all these red carpets, but it doesn't matter. It's the same on the internet. It's like,
So it's in that.
it's the same dynamic, just playing out in a digital space. It's very good.
So good that that doesn't have. We still have the first.
All right, how are you drinking?
Let's see what happens. Let's give a couple of minutes.
I also tried to keep this short. I know that I'm the last one of the semester during the report final.
I don't think so, not that they told me about. Not for them to sign or anything.
No.
It would help for people on Zoom, though.
Do we have?
Yeah,
It is on Zoom.
we usually have about like 10 or so.
If I wiggle a mouse right here, will I be able to see? It's on Zoom? Okay, it's because my device is hosting, isn't it? You know, I rolled my mouse up and I'm not actually seeing the Zoom bar. Did we fall out by chance?
I mean, we didn't fall out. I just hid them.
Oh, escape hides it. I had no idea.
Just hide the floating panel.
Oh, and what mic is this using? Is this using my laptop mic?
No, it's using this mic.
No, this says Realtek audio right here.
I tested the audio.
Test 1, 2, mic test 1.
Can anyone in the Zoom chat or anyone in the Zoom hear us? Can you guys hear okay?
Yes.
Thank you.
Great. Okay.
All right, there we go.
All right, so
Did
we
it-
have,
Give you this while I get the slides back up.
welcome everyone. And as we get started here, it is my pleasure today to introduce Dr. Matt Caplan, who is an associate professor at Illinois State University. He was previously a postdoctoral fellow at McGill, and his PhD from Indiana won the 2018 APS Dissertation Award in nuclear physics. Congratulations.
Thank you.
He has a broad interest spanning nuclear physics, plasma physics, and astrophysics, and received the Cutler Scholar Award in 2023. Beyond academia, Dr. Caplan is also a scriptwriter for Kurgesat at PBS and PBS Spacetime. He has written some of the most popular videos on YouTube about nuclear weapons. That's our interests converge. And the videos he has worked on have combined view count of 1 billion. So please join me in welcoming Professor Caplan today for his talk on how plasma splits.
Thank you so much for that introduction. Before I start, I want to do a little bit of crowd work. Anybody in this room have a favorite equation? Everybody has a favorite equation, right? You guys see a hand? Who has a favorite equation? Right, and then if you have a favorite equation and you aren't afraid of public speaking, please keep your hand up. Really? All right, so who are you pointing at? Who are you picking on, Katie? Who's my?
Go for it, Silvana.
Is your name Silvana?
Yeah.
My name's Matt. It's very nice to meet you. Are you a graduate student here?
Yeah.
That's excellent. What are you a graduate student in?
Sorry, what?
What are you a graduate student studying? What's your work on?
Oh, I worked on transfer.
Neutron transport. What's your favorite equation?
Transfer.
Neutron transport equation. Why? What about that makes it your favorite? What's interesting about it?
Oh, I feel like.
Don't know.
I
That's
just love
okay.
it.
That's okay. Anybody else? Again, this is a safe space. This isn't being recorded for posterity. It is. Yes, young man, what's your name?
I'm Kevin.
Hi, Kevin. I'm Matt. What's your favorite equation?
Also the neutron transport equation.
Why is the neutron transport equation your favorite equation?
I like the mix of hyperbolic, elliptic, and parabolic behavior it yields.
Ooh, that sounds smart.
Math for saying that it's very weird depending on the materials you're trying to simulate in.
I love that. So you get a lot from a little, is what you're telling me.
Pretty much, yeah.
So I think that if you ask almost any scientist or any engineer, you're gonna get an answer like that, where they're gonna say it's a compact, simple thing that you can write down, and then it's gonna spiral out of control and complexity, and you're gonna get some really cool, dramatic stuff depending on how you start tuning your knobs. The rules of chess can be written down in a page, and yet you get this giant unsolvable like set of strategy that comes out of it. And so that's what I want to do today. I want you to just sort of forget that you're a plasma physicist or a nuclear engineer, any of these things. And I just want you to go on a little ride with me as I tell you about one equation I find really cool and this really interesting game of chess that kind of comes out of that. So I know that this is the week before finals and people are not totally engaged. So let's keep it light today. Let's just have some fun and learn about this guy. Do we recognize this guy? Do we spend a lot of time with him in our coursework or her? I don't know. Equations don't have genders, right? Do we recognize this? What am I looking at? What did I put up here? This is the Coulomb potential, right? This is a charge is always Q, 4 pi epsilon naught, that's something Coulombic. And then there's an R, so this is a potential, not a force. And then there's an exponential here, so that's a screening, right? That makes it drop off. This is the screened Coulomb potential. This is foundational in plasma physics. And it can be written so simply, and then from something so simple, you're going to find all of the really cool things I want to show you today. So we're very used to seeing 1 over R potentials. Everybody sees this as a high school student. Oh yeah, there's this big ramp that goes to infinity at the origin, but then when you're really far away, it goes to 0. We're all very used to that. But when you add this exponential, this screening, if you say, let's put some other diffuse charge that would tend to neutralize your central point charge when we're far away, you soften the potential and you get something like this. So depending on this, which can be your Debye length, or it can just be any sort of screening, you're going to take this red curve and you're going to start to drag it down and inward. So it'll go to 0 faster. That's the whole point. That's all I want you to come away with. Very simple classical potential that we could, again, teach to like a high school student if we had to. Again, we're high school students today. We are not overthinking this. We're not doing plasma physics. Yes, these are balls rolling on hills, right? Every potential is secretly just a roller coaster track. Ball goes up, loses kinetic energy, slows down, turns around. So if I have a ball with some kinetic energy or some speed, it's going to roll up until it hits a certain point on the hill. It's going to stop. It's going to be all potential energy. It's going to turn around. It's going to go away, right? High school physics, we all get it. Notice how if the potential was screened, it would have made a closest approach. That's really all I want you to take away from this. There's really only one knob in this potential, and that's the screening length. That screening length ends up doing really important things for the dynamics of 2 interacting charged particles. I am being so boring right now. I'm telling you stuff that we all learned, like, not as high schoolers, let's be honest, but at least in some of our intro electrodynamics. I care about this because I'm a physicist. Okay, people want to know about supernova, they want to know about cool fluid dynamics, they want to know all these big things, but you can't do big things without small things. Microphysics sets macrophysics. The entire dynamics of a chess game follow from the fact that pawns move 1 step forward, but they capture diagonally. If you change that one rule, the entire strategy of chess changes. In the same way, if you change anything about how plasmas behave at this fundamental level of how 2 particles come together and then move apart, you change plasma physics. So I'm going to start with this really simple sort of collisional dynamics. And from it, we're going to construct really interesting emergent behavior. That's what physicists do. I'm so sorry. I'm a physicist, not an engineer. I wish I could tell you something you might be more interested in, but let's just take a ride. Let's do some microphysics and see the macrophysics that comes out of it. Have a big ensemble of charges. Maybe it's in a plasma fusion reactor. Maybe it's in a star. Maybe it's in the interstellar medium. It doesn't really matter. We can be dimensionless. There's some density, and that density sets a mean separation. And obviously, some will be a little closer together in the process of colliding. Others will be at a different stage and will have a different separation. But you have a mean density. Think about the potential as you start to put all of these potentials together to build a map of what the potential gradient looks like, where everyone lives. So this particle right here that I'm sort of drawing attention to in the middle has all of these neighbors that create big spikes like this, creating a little potential well. Every single charge lives in a trap that is created by its neighbors. This isn't news to people. Maybe it is. Maybe it's just a different way of thinking about something you've seen before. But this ends up being important when you think about the collisional dynamics. How does the kinetic energy compare to the mean potential energy? Now we have a second knob. Beyond just density or screening length, we have the temperature. If I cool this system down, where is everybody going to go? They're going to settle into a lowest energy state where they're going to be trapped. And these traps have a lowest energy packing, and that packing is crystalline. My punchline, which I'm giving away 10 minutes into a 15-minute talk, is that plasmas freeze. It doesn't matter how hot it is. If the density is high enough that the Coulomb energy vastly beats the kinetic energy, they will not move past each other, and you will have frozen a plasma. You can be so hot or so dense that you have fully ionized nuclei. And it won't matter because you're at such high densities that they do this. The only place that you might encounter this in your normal coursework as nuclear engineers is the idea of a dusty plasma. As they went on the International Space Station, they took literal dust, like powder, and then they put charge on it, and they find, oh, look, they can make the dusty powder do this. Given the density, given the sort of kinetic energy of those particles, they can get dust to do this. There's one other place in the universe that this is going to happen, and this is going to be inside stars, and that's sort of why I do this. Uh-oh, big, complicated, scary phase diagram. Show of hands, are we familiar with this? Do we encounter this in a lot of our coursework? Yes? Okay, other show of hands. Who has never seen this before in our lives, and this is scary? Okay, might be a little scary. Maybe you've seen it before. Okay, two axes. Before we even think about the contents of the plot, think about the two axes. Here's temperature, and here's density. If you're a chemist, you live sort of right down here. Everything has a density of about water, about 1 plus minus an order of magnitude. And you never push temperatures more than a few hundred, right? That's room temperature conditions you achieve in a lab, right around here. But matter can be at all of these conditions, depending on where you are. If you go to really low densities and really high temperatures, you're in the solar corona. If you go to densities of a little bit more than water, you actually pressure ionize. You have this conduction band of electrons. And if you keep pushing, you fully pressure ionize. You cease to have electron orbitals at all, like the conditions inside of a star. And you push to plasmas that are really high density and also really high temperatures, for example, like the solar core. But there's a line that you can draw on this, is you can ask, how does my potential energy, determined by my position on the density axis, my distance to my nearest neighbors, which sets my Coulomb energy, compare to my thermal energy? Which one's bigger? Do I have more thermal energy or do I have more potential energy, especially in these sort of ionized, pressure ionized solids? And there's a diagonal that you can draw. This thing, gamma, is a ratio of your characteristic potential energy to your kinetic energy. Again, I'm a plasma physicist, and this is like very normal for me, but I wanted to be introductory in case this isn't normal. Do we encounter gamma, the coupling factor, in our coursework here? That sounds like a no. Was that a big resounding no from everyone in this room? This is a no or a yes. I saw this little hand. This is a yes, we encounter this. Have some fun, guys. This doesn't matter. Like, let's again, no, never seen this before. Don't know this thing. Great. It's a ratio of energies. It's a ratio of telling you who wins, potential energy to trap the particles or kinetic energy to let them move past each other freely. A huge part of this parameter space, pressure wins, density wins, and particles will not be able to move past each other. So these are still solids. You can extend this line. You can say, hey, there's going to be solids out here that are fully ionized plasmas. But I don't have any pictures on here, and that's because these are going to be white dwarf and neutron star cores. So these are such high density spaces, 10 to the 8, 9, 10 grams per cubic centimeters, that you get crystallized plasmas. Again, this is not relevant to a reactor. You're not going to be using this to make energy, but it does turn out to be a physically real system that has astrophysical implications. And I see a hand. Yes, sir.
Are these plasmas fully ionized?
Yes, they are fully pressure ionized. You have a degenerate electron gas. In fact, you can completely discard anything you think you know about electron orbitals because the nuclei just become point charges in a Fermi gas. So it is, in fact, one of the simplest plasmas you could ever hope to encounter. I'm going to tell you about this space out here. Let's try and get some movies going. Here's my gamma axis, my ratio of kinetic energy to potential energy. This is just another way of writing it. If you turn up the charge, you get more potential energy, but that can be countered by increasing the temperature. So ultimately, a dimensionless system is enough to understand this. One knob, gamma. It's a proxy for temperature. At high gamma, you have high coupling, and you freeze. This isn't an artist's take on it. This isn't, something that would be rendered in Hollywood. This is a physics simulation. And these are point charges that all repel every other point charge. And yet, even though it is a purely repulsive potential, when you put it under pressure, when you put it in a box with periodic boundaries, you actually get a solid out of it. Increase the temperature, and you get something that's ideal gas. So I spend a lot of time in rooms with like plasma astrophysicists, people who care about neutron star magnetospheres and magnetars and fast radio bursts, and all this really cool, sexy stuff that the public wants to know about. And they all talk about collisionless plasmas, where the dynamics are driven by magnetic fields. But then you go to these really hot plasmas and you go, oh, well, we do have this sort of ideal gas-like set of collisions. If you push to high enough density, you get super collisional plasmas that are bumping into each other so much, so many times per second, that you can't do this analytically is you need supercomputers in order to do simulations to extract the microphysics, the transport coefficient. Diffusion is essential. We care about how these materials, about how they can rearrange and how they can separate. In liquids, this is easy to do, right? It's Brownian motion, but in solids, it's hard. So I'm here to spend another sort of 20, 30 minutes bragging about how we have finally cracked diffusion in a solid and what this can mean for material properties like the elastic properties of neutron stars and white dwarfs. I'm not going to tell you about stars though, because you don't care, because this isn't an astronomy colloquium, so I'm going to keep it dimensionless. And I'm going to stick with this. Do we do this in our courses? Brownian motion, right? You have a bunch of particles. When they're hot, they bump into each other. They travel like an ideal gas. Pick one of these orange balls. That's to guide your eye. Those are just tracer particles. They'll all diffuse at their own rate. They all have their own random walk. But if you average all of those random walks together, you get a line like this. The slope of that line is the diffusion coefficient. The slope of that line tells you how fast this material mixes, how fast it flows. Make it hotter, this thing sort of becomes steeper. Make it colder, the slope of this line goes down. But what happens if you make it so cold that no particle ever leaves its home base? They get stuck on a lattice site. Diffusion in solids is really hard. If any of you work on this, you have my commiserations, because this is one of the hardest problems I've ever tried to tackle in my career. There's very few in the way of the analytic approaches that are sort of tractable to do this when stuff doesn't move off of its lattice site. Pick your little orange particle, it's not going anywhere. This is projected flat in 3 dimensions. And if you just stare, they're not moving off their lattice site. Okay, so what is diffusion in a solid actually like? Watch closely. Let's zoom in. Let's slow down. Watch very, very closely. They wiggle. They're on lattice. Nothing interesting happens ever. This is so boring. Why am I wasting your time with? What is that? Goodness gracious. Did everybody see that? Did my vision go blurry for a second and they made those smudges? What was that little set of diagonal racetrack lines? And there it is again. Golly gee willikers, Batman, what's happening? And it keeps going. What I'm seeing is diffusion in a solid. Diffusion in a solid is a completely different process than diffusion in a liquid. Diffusion in a solid is a highly correlated lattice process where particles exchange places with their neighbors on a lattice. Very unlike the ideal gas-like motion you get with the Brownian motion in solids or liquids and gases. And so unpacking this and finding actual transport coefficients for a material like this requires really, really long simulations to resolve just a few of these interesting little events. So should we do that? Should we try and learn more? Ultimately, this is the question. A couple of astrophysicists called me and they're like, help us, Matt, you're our only hope. And I said, I hardly think that's the case. You guys are much smarter than me. They're like, yeah, but you know a little bit about plasmas and materials. What are the diffusion coefficients? We need to know how these solids can flow if you put them under stress, what the elastic properties are. We need to start with the microphysics. So diffusion coefficients, we need to know how diffusion coefficients depend on gamma, that coupling strength or temperature, and also the screening, how different electron screening changes how the solid will flow. Those were the big questions. I got a phone call, and not really as sort of for dramatic effects. And it says, Matt, what's the answer? Here's a unit cell of a crystalline solid. It forms a body center cubic lattice, funny enough. This is the lowest energy state. How is this ever going to move off of its lattice site if all of the lattice sites around it are occupied? Well, it starts with thermal activation, like almost everything in every material and chemistry does. You need a large enough oscillation of the neighbors on their lattice sites to lower the potential barrier here while you have a large thermal oscillation of this guy in the middle so that he can move through. So everything's thermally activated, is my main point. But you cannot move off of a lattice site unless a neighbor has also moved off of a lattice site. So this is a correlated many-body process. This is not something that's just as simple as thermal activation. There's something else going on. So I'm going to introduce a little visual language before I show you any more simulations. I've showed you 3 or 4 simulations of solids already, but now I want to introduce a way of thinking about diffusion. What are you looking for in diffusion in a solid? You're looking for particles that have moved one lattice spacing. If you're just seeing thermal noise on a lattice site, that's not diffusion. So run a simulation and make a cut and say, hey, show me a list of all particles that have moved by a lattice space or most of a lattice space. Most of them are going to look like this. It's just going to be large
thermal oscillations on a lattice site where they started at a thermal maximum in one direction and they ended up at a thermal maximum on the other side sometime later when you take another snapshot. This is uninteresting. But what happens if one of them makes a large oscillation on a lattice site, and in doing so creates a big enough opening for another one on an adjacent lattice site to fall in and steal its lattice site? What has happened here? Does anybody recognize what has formed in this image? It starts with a D and it ends with an effect. It's a pair formation event of an interstitial and a vacancy. This particle fell off the lattice, a neighbor fell in, you now have a vacancy here and an interstitial here. The vacancy migrates by having neighbors fall into the vacancy, they separate, while the interstitial likewise migrates. And if you look for particles in a simulation that have diffused by more than one lattice spacing, you end up seeing this cascade of diffusion all happening at once, just like that animation I showed you a minute ago. Diffusion doesn't happen one at a time, it happens a whole bunch in sequence before eventually they sort of find each other and the whole fills in. And you can have very rapid exchanges. If everyone thermally activates to take a neighbor's spot at the same time, you can move in a loop, all within one sort of plasma oscillation, all in one sort of step at once. So now that I've introduced this language, I want to show you those simulations of solids again, but I want to show them with all of the particles removed. And instead of showing you nuclei on a lattice, I'm going to show you arrows. I'm going to show you displacement vectors so you can see which particles have moved. All right, this is a simulation very near melting, right near the melting temperature, but it is solid. This is a crystal. It has some relatively weak screening, just a little bit of screening. This is going to be a histogram showing you the displacement of the particles. Everyone is displaced by less than one lattice spacing. That's how you know they're all in their home base. They're at their initial conditions. This is a 3D volume that's going to rotate, and then these are projections along each of the axes. So if you see down here, I have the axes at the corner of the box. This is unfolding the ZY, the ZX, the XZ sort of faces of the box. And this is going to show you the average displacement, basically the track of Brownian motion. Let's let it play. Lots of thermal noise. There's oscillation on the lattice, but then all at once, a chain forms and rushes through the simulation. And there's two of them. You see there's two snakes. It's kind of hard to tell. Adjacent to the snake, you get lots of these little loops until eventually the snake eats its own tail. The interstitial has found the vacancy again and annihilated it. It's all gone away. Occasionally you get some of these little loops, but for the most part, nothing. And it's quiet. There's a period of quiescence. So these thermally activated defects, they take a long time to form. Many, many thousands of plasma oscillations in a simulation of this line. But then once they get going big. So what we're seeing is, hey, look, here's the diffusion coefficient when you have defects active, that's this slope. And then in a period of quiescence, it flattens out. But if you were to take the average over the whole simulation, if you were to draw a diagonal that's the mean slope of this line with all of those periods of quiescence and diffusion put together, you get the diffusion coefficient. It's very straightforward, like introductory statistical mechanics or chemical physics. Does anybody else notice anything about the little red loops? This was something I missed the first time I watched this. The red loops always tend to happen, or for the most part, they're more likely to happen next to the chain. It's almost like an interstitial or a vacancy passing catalyzes those loop hops, as if having the defect makes it easier or lowers the energy threshold for one of these loop hops to happen. Like you see 3, 4, 5, 6, 7, 8, 9 of these loops, and then you see none. And there are no interstitials or vacancies. It's a nice little observation, isn't it? And as we approach the end of this simulation, if I draw your attention back down here to the corner, hundreds, maybe even 1,000 particles have all diffused in this box. We have good enough statistics, we can actually extract a diffusion coefficient. Just throw computer hours at it until statistics come out. That's how computational physics works. Go teach your class, come back at the end of the semester, do some analysis, and you get a plot out of it. This is also a very natural time to pause and see if there's any questions. I know this was a lot of information very quickly. Yes, please.
Experimental.
I hope so. This is all simulation data. Oh, yeah, one more.
What is the real time of the simulation?
Like the wall time or?
Like how long do you have to wait and what does it actually represent?
Yeah, this guy is a GPU day with 16,000 particles, which is fairly good, if I do say so myself, 10 milliseconds per time step. The physical time is all scaled out. This is all dimensionless. So I don't have an answer for that. Pick your favorite temperature and density, and I can tell you. Remember what I said about screening? Remember how I said if you have a strong lambda in that exponential, you soften the Coulomb potential? That's what this is a plot showing. I'm showing at stronger screening, if you push up to these redder colors, if you screen the plasma very highly, that potential drops off very quickly, meaning you have lowered the Coulomb energy to nearest neighbors, meaning the crystal freezes at much lower temperatures. So the diffusion coefficients, as you push to really high screening, end up spanning many orders of magnitude just by tuning this one knob in screening. But you notice there's a trend, like increasing the screening pushes you out to diffusion at these much higher gammas, much higher coupling. The question that a plasma physicist would ask is, plasmas have a tendency to all be the same. There's this tendency for universality among plasmas, where any time you find something like this, there's a transformation, a choice of coordinates, a fit that makes it all go away. So this becomes a question of the melting temperature. If you screen a plasma, you change the melting temperature of that plasma because you've changed the Coulomb energy. So here's again your relationship between your Coulomb energy and your temperature, your kinetic energy. What if you scale out how the energetics changes because of the screening? So this is a melt line. This is actually a phase diagram. I'm showing you the screening here. If you push a high screening length, you push to colder melting temperatures. This has actually been known for like 25 years that you can freeze these solids. This isn't like anything new, I'm telling you. That's a very old thought. But take this, and instead of using this coupling factor, this ratio of kinetic energy to potential energy, put in a Taylor expansion for the screening and rewrite it in terms of this melting temperature. So now I'm going to have a new screening factor or a new coupling factor. This coupling factor gamma is now going to be 1 or greater for solids, and it's going to be 1 or less for liquids. It's a doubly dimensionless coupling factor. It sort of gets rid of all of this information about screening and sort of bundles it into this one number. If you do this and put it all together, you get a nice Eyring model where all of these lines collapse into one. Ta-da! Fireworks moment! Popping champagne! This was really big. The first time we generated this plot and did this fit, we were like, we did it, we got it, we have cracked something in plasma physics. And the answer is because we did. We turned all of this into 2 numbers. And if you have these 2 numbers, you can pick a plasma at any temperature, any density, of any nuclear charge, and I can tell you the diffusion coefficients in its solid phase. This didn't exist before, and it exists now. And so we're very proud of that, because that's how science works. You got to do something new if you're going to publish it. We were so proud of this, we submitted it to physical review letters. And of the 3 referees, 2 of them were very positive, and we managed to convince the editor to publish it. But I say we because science is never a solo endeavor. There are always students, and I think it's very important to acknowledge when all of the work is done by the student and none of it is done by the professor. And this is the student. His name's Danny Yakub. Are there professors in the room? Faculty, please raise your hands. He has expressed interest in doing a PhD. He will be graduating at the end of this year. He is applying, including to this department. Keep an eye out for his application because he's very good. He made all of that. To the students in the room, I hope you are finding yourself working for professors who would do the same for you. And if not, shamelessly ask them to do this. If people's like, can you put my face on there and tell them I want to come here for grad school? One of the things I didn't show you in that last plot is how interstitials and vacancies independently diffuse. You notice that when there were green chains, there were 2 of them, but I couldn't pick out which one was the interstitial and which one was the vacancy. So obviously they have different diffusion coefficients. The energetics of an interstitial are very different than the energetics of a vacancy because they distort the lattice around them in different ways, meaning they will migrate at different rates. So there's multiple energies here. There's not just an activation energy for diffusion. There's an activation energy for pair formation, and then there's activation energies for the individual defects to migrate. And so we want to isolate those as well. So the simulation I just did is this one. I guess I'm using my shadow instead of the laser at this point, but this one all the way on the left, where you always have equal numbers of vacancies and interstitials. In that simulation I just showed you, I had always one vacancy when I had one interstitial, meaning it was impossible to separate out the relative contribution to diffusion from the vacancy and interstitial. It's very hard to look at one of those chains and know what's at the end of it, especially when, you know, it's just sort of, they make a mess of their local environment. It's not so simple as it is in this cartoon. All of this space around these defects distorts. It's very hard to pick out which end is which. But it is very easy to go into a simulation with a perfect crystal. And since I'm a wizard, I control what happens in the simulation. I can pluck a single particle out of the corner of the lattice, and I can artificially induce a vacancy. And then I can isolate the contribution of a vacancy to the diffusion coefficient in exactly the same way I can go in and I can add an interstitial to a lattice. So do a simulation with n defects, or excuse me, n particles, a simulation with n-1 and a simulation with n+1. Fit the slopes of those displacements and you get diffusion coefficients independently for vacancies and interstitials. I was really proud of myself when I thought of this because like, ooh, I am so clever. And then I typed this into Google, and material scientists have been doing this for years. Someone in this room probably did this for like a class project at some point. So anyway, every good idea has already been had, is sort of the moral of the story there. But I thought of it without Googling it first. And for that, I'm still really proud of myself. This is a simulation not with 16,000 particles. This is a simulation with 15,999. What do we notice is happening in this simulation? I notice one snake instead of two at all times. It's never going away. I also notice that sometimes it gets really active and it gets very fussy. Not right now, but give it a second. There we go. It's very, very excitable, isn't it?
Periodic boundary?
Periodic boundaries, yes. I'm sorry I didn't clarify that sooner. You see the snake come up one side and come back? If you look at the curve of the displacement, you notice that there are now two slopes that are showing up. Do we see that? But there's two different sets of slopes that show up here. So instead of having a period of quiescence and then having periods where an interstitial and vacancy are active, we have periods where one vacancy is active, and then we have periods where two vacancies and an interstitial are active. Why is that interesting? It means that I get two numbers. I get two slopes here, don't I? Two variables, two unknowns. This simulation is enough to get the diffusion coefficient independently for vacancies and interstitials. The diffusion coefficient for a vacancy is this slope, whereas the diffusion coefficient of a vacancy and two vacancies and interstitial is this slope. So do a little bit of subtraction, do some high school algebra, you get these two slopes give you the two diffusion coefficients. It's very simple. It's like such a simple technique that reviewer 2 could never say that this is dumb. They could never say it's impossible. Finally found a way to outsmart the reviewers. Haven't actually submitted this yet. This is in the next paper that we're going to send out. Take a guess. Like, I guess I have the plot up here, but what do you think is fastest? A vacancy or an interstitial? Like, show of hands for a vacancy. Show of hands for an interstitial. Everybody knows an interstitial is faster. Is this common knowledge among chemists? On these plots, it's very obvious that the interstitial is faster. That's exactly the opposite of what I would have expected. I had this idea that a vacancy, it's like, oh, well, there's a void and it's very easy to fall in, whereas an interstitial has to push a neighbor out of the way. But the data doesn't lie. I mean, this slope is definitely bigger than this slope. So the interstitials are faster by about almost a factor of 2. So presently, this is the extent of this sort of set of work that I've got. We did some pilot runs. But we're doing a survey right now across temperatures, screening factors, and we hope to have a relationship that can generate the ratio of interstitial diffusion to vacancy diffusion by the end of the year. So had I been giving this talk closer to New Year's, I would have had that result, but none of you would be in this room because you're going to go home and take some time off. So here's the preliminary work that's what's coming. Oh, I had these two slides out of order. I was going to do a little vote thing, and then I was going to give you the answer, but clearly I did it backwards. Interstitials. Interstitials are really cool. I have decided that they're my favorite, even though I started thinking that it was all about vacancies. Turns out it's all about interstitials, man. Fundamental fabric of reality is interstitial defects. This is my simulation with 16,001 particles. I showed you the vacancy a minute ago. Now I'm showing you the interstitial. What do you see here? What's going on? The interstitial is not just as simple as saying, I'm going to drop a particle and it's going to just sort of fit into the lattice and just sort of fit in an interstitial space. It actually pushes out a column of nuclei along the body diagonal of the BCC lattice. So even though it's sort of hard to see the depth here, all of these particles that misalign with the lattice are part of the interstitial defects. The interstitial is not one particle, it's a quasi-particle of 5 or 6 in a row that together become this larger scale defects. You go to cold enough temperatures. Yes, please.
So instead of like moving in the gaps between where the lattice points are, is it like a Newton's cradle thing going across?
It is exactly like a Newton's cradle thing. So there's not one that's moving, it's an entire stack along the lattice that seems to be moving. Does anybody know the name for this? I had to look it up. I'm learning material science in real time in order to do the material science plasma physics. Has anybody, do you know this? Like, it's called a crowd ion, is the name given for this kind of quasi-particle where you fit 6 nuclei in a space where you would otherwise have 5. It has a name, and like semiconductor people are obsessed with it because apparently it's important for, I don't know, silicon. But here it is. What happens if we run a simulation of this? We're significantly colder, so we're at about 1/6 the melting temperature here. The simulations I showed you earlier were very near the melting temperature. And again, you can't tell the vacancies and interstitials apart because they worm their way through like snakes. Notice what happens in this simulation. I'm going to just stop talking. I'm going to let you take it in for a minute. Yes, you. What's your name?
I wasn't raising my hand.
I know, but we're doing this anyway because. Hi, Angela. My name's Matt. It's nice to meet you. What do you notice that's different about these, aside from the color? We color the areas differently than the simulations before.
So we don't have the lattice structure and all that.
Yeah. So we see the lattice structure because it's sort of following these diagonals in the box. But what else are we noticing?
And also there's loops. We have many different loops rather than just the two that we have.
Yeah. Let me run this again. Yeah. So the oh, come on. The hops, these diffusive hops, are highly correlated. Those snakes that I was showing you a minute ago, once the defect had moved by a lattice spacing, it was basically rolling the dice to pick which of the neighboring lattice sites it was going to move to. But now, the crowd ion, because it forms this sort of long quasi-particle, it is much more likely to move forward than it is for it to rotate and move onto a different diagonal or a different stack in the lattice. So again, you have this diffusion, you sort of put a slope through this, you just sort of pick the average slope here, that tells you the diffusion coefficient, and you get a diffusion coefficient for the interstitial. But it tells you that even though interstitials and vacancies have different activation energies for migration in the crystal, an interstitial also has more than one activation energy. It has an activation energy for forward and backward motion, but then it has an activation energy for rotation and turning and moving a different direction on the lattice. And clearly, they are different and have different temperature dependencies. This is colder than those simulations I was showing you earlier, and we're seeing that the forward-backward motion is very easy now, while the turning motion is being quenched out. You're freezing out the turning of these defects. How neat is that? Let's go colder. Do you want to go colder? She said yes, so I'm going to do a simulation where I go colder. Thank you for anticipating my next slide. I have halved my temperature again. I was at 1/6 of melting. Now I am at less than 1/10 of melting. Heck, it's periodic. It never turns. It stays on the same diagonal forever, and it never turns. This is a one-dimensional random walk. It goes forward, and then it goes backwards, and then it goes forwards, and maybe goes forward for a while, but eventually it turns backwards. And anybody who knows the dynamics of a one-dimensional random walk knows that it always comes back to the origin. Oh, look at this. Yeah, it's going really far in one direction right now. And oh, look, that's inflating my diffusion coefficient. But as soon as it ends up back where it started, it ends up undoing all of those diffuse pops. So it's like you've taken a stack, you've moved it forward, but then you sort of eventually move it back. Or you move it so far forward that it comes over the periodic boundary and you move it back into place anyway. So the diffusion coefficient is garbage here. You can't actually extract a diffusion coefficient this cold, even though you see diffusive hops. Yeah, you're thinking, I see this look on your face. You're like, I had an idea. Before I tell you that idea, I want to ask a student in the room, have you ever had an idea fail? Yeah, you do stuff all the time. It just doesn't work, right? I want you to know, like, this is real professional advice that never stops. You never stop having bad ideas that you sink a week into that go nowhere, and you should have seen it coming. It never goes away. So I think it's important that we don't just come up in these research talks and show you successes. I think it's honest to show you failures, because research is not a linear process. It has lots of dead ends, and it's only after we have pruned those dead ends from the bush of research that we're left with our nice, pretty flowers of results that get accepted to journals. Most stuff never sees the light of day, and I think that's a sin because, well, a lot of really clever things happen on those dead branches of research. This is the lattice I was simulating a minute ago. You have periodic boundaries, and that periodic boundary came across this diagonal. It went on a tiny little diagonal right here before coming right back to that same diagonal. I had a great idea. I was like, hey, I know the Pythagorean theorem. I know that this is 40 lattice spacings. 20 by 20 by 20 times 2 is 16,000. And 40 is a nice Pythagorean multiple. I can rotate the crystal by the angle of a 3, 4, 5 Pythagorean triangle, and I can still perfectly tile this volume. Only now, if I pick out my crowd ion, now it's here instead of right there, it now has a much longer racetrack. Because now it sort of goes over the periodic boundary many times. And I was like, this is so clever. I'm so smart. I'm so good at my job. That was my idea. And I was like, this is going to allow me to actually get the diffusion coefficient because I made the racetrack longer. I didn't have to push to a larger simulation size in order to get it. And it's just applying a rotation matrix. Except I'm a big, dumb, stupid idiot who forgot that none of that is going to change the fact that this thing doesn't turn. So it doesn't matter if my racetrack is longer. It's going to go forward. It's going to go backwards. It's going to go forward again. And it's going to end up where it started. And I'm still going to get garbage data for my diffusion coefficient. It's going to be all over. It's a nice try. Good attempts. Feel sorry for Danny. He's the one who had to apply the transformation, run the simulation, and animate it. He was a good sport about it, though. I promised him I would show it so that all of his work on this wouldn't go to waste. He learned a lot about rotation matrices in the meantime and not believing everything I say. That's maybe the more important lesson. You know, I asked him, hey, Danny, what should I say? I'm presenting this, but this is what you do when you advise students. He said, how do I explain this when I'm there? And it's not because I need it, it's because I need him to get the practice. Because what do I say when I show this plot? And he said this. This was his joke, not mine. I'm not that funny. He is. Again, look at him go. Roaring and soaring. We're going to get a follow-up paper about this submitted very soon. I had this on my title slide. All of this work that I just showed you is funded by the Simons Foundation because neutron stars. But all of these techniques, all of this math, if you just push to a slightly different temperature, slightly different density, you can do really interesting plasma physics. So I promise I would give one slide that's maybe of more practical interest to this audience. When you have a plasma and everybody's bumping into everybody else, you end up having inhomogeneities in the charge density. Little pockets where collisions are happening, where you get slightly more charge, slightly less charge. This creates micro fluctuations in the electric field. And, spaghetti-o.
Hey, Christina, get the microphone stuff.
So,
I'm out of batteries in my microphone. I'm so sorry to everyone on Zoom. I don't know why I'm saying this right now. They can't hear me.
let's try that one. Sorry.
Doe, a deer, a female deer, ray, a drop of golden sun. If you have particles moving around, you get tiny little micro fluctuations in the electric field. If this is not fully ionized, if we leave a neutron star and we move somewhere more interesting, more practical, like a fusion plasma, those fluctuations in the electric field are going to create fluctuations in, I don't know, spectral lines. That's going to create variations with temperature and density in radiative transport, in opacities. And sure enough, this stuff is actually unsolved in certain relevant parameter spaces. Fun fact, not everything is known that we need to know about the universe. So this was just funded. We're very excited to be starting this partnership in 2025 with Lawrence Livermore National Lab to use molecular dynamic simulations to calculate microfield fluctuations to determine radiative opacities for reasons. People used to laugh when I would switch to this slide, and maybe I'm getting too old to be. Do we know this reference? Okay, thank you, those 4 of you who laughed. Monty Python and it doesn't matter. Monty Python. I want to use my last a few minutes to just tell you about some totally different stuff, because I think that it's good that we, as academics, are holistic and we do things other than just sit at a terminal and make plots. During the pandemic, I was one of the inaugural fellows of the Physicists Coalition for Nuclear Threat Reduction. Show of hands, who has heard of this? Excellent. Well, I'm sure you'll be getting an email soon enough from Angela advertising the Physicists Coalition Next Generation Fellowship. So the Next Generation Fellowship is intended to train physical scientists, that includes you as plasma and nuclear engineers, in nuclear weapons policy. This is important. There are 12,000 nuclear weapons on Earth. These weapons are owned by 9 nations. In less than the time that we spend in this room today, a crisis can escalate from non-existence to annihilation. There are 15-minute launch timescales to get an ICBM from out west to Moscow. This is terrifying, and it terrifies me. And we as a country need to do better. The United States needs to be showing leadership. And that means people like us, smart people in this room, need to be trained in order to talk to congressmen, in order to talk to people who make policies, to advocate for these sane, common sense changes to US weapons policy. So they trained me, which was awesome. And real things come out of getting trained in this. I just finished a limited podcast series on NPR leading up to the election with Lauren Warnicki titled 12,000 Bombs. You can go listen to it. It's actually finished, so I'm not just doing this to get my view count up. But some very interesting people are on there, including Fred Lamb from UIUC. They have a nice talk about ballistic missile defense, literally the week after Iran's missile attack on Israel. So we got all the current events in here. It's admittedly was framed as an election issue. That's how I managed to get the NPR affiliate to produce it. So some of it might not age as well as it could. This is Shelley Lesher. She's a friend of mine who came to speak as a part of a companion seminar series at ISU that we held. She has her own podcast. Her podcast is called My Nuclear Life. It is the largest dedicated nuclear issues podcast on podcast. What is the podcast space called? My Nuclear Life. I did an episode with her to return the favor of her coming to give this talk. And it's about where we should bury all of the nuclear waste and what the far side of the moon has to do with that, and radioactive glow-in-the-dark cats have to do with that. If you've enjoyed the sound of my voice for the past 48 minutes, that's where you can hear more of it. How is he still going? Something Angela mentioned at the start is that I also do a lot of popular science communication on YouTube. YouTube is saturated with entertainers, Bill Nye types, who want to go out and tell the world about cool science, but many of them are not trained scientists themselves, and they need smart people, again, like you, to act as interpreters, to translate the technical things that are happening in a place like this to something the public can understand so they can be informed. Some of them are, kind of ridiculous. What if we detonate all nuclear weapons at once? What if we nuke the moon? But some of them are really informative about space exploration. And so I've been writing for Kurzgesagt for about 10 years now. And sort of the reason I'm advertising this is because I like to hear your ideas. If you ever go on YouTube and you're like, man, I have a cool idea. Like, wouldn't it be neat if there was a YouTube video about this and it could show it this way? I'm around tomorrow morning. Send me an email, come pitch me your idea. All of my best ideas come from having too much coffee with smart, interesting, early career people. That also includes PBS Spacetime. For those of you that are a fan of the more esoteric quantum mechanics and cosmology, these are all things that I've sort of worked on within the past year or two. And some of them are, again, a little bit more esoteric than others. But if you have a technical story, something really neat about fusion energy that's in the pipeline that the public doesn't know about but could, send me an email. My job is to turn your cool research stories and colloquia, sort of like the one I just gave, into things for the public. And I wasn't lying or bragging when I say I have a combined lifetime view count of 1 billion. I'm saying that to entice you to tell me your story so I can help you tell it. And now back to our regularly scheduled programming. I want to end with one final plot, one final animation. Early in my talk, I told you the diffusion coefficients are universal. In some sense, everything about the screening length scales out and it's somehow all the same, it's one curve. And I also want you to know that was a lie, because there's something else that happens. So I'm showing you a grid of 4 simulations. 2 of them are very near the melting temperature, and 2 of them are a little bit colder than the melting temperature. 2 of them are at low screening, and then 2 of them are at high screening. So these 2 should have basically the same diffusion coefficient, while the 2 on the right should have a different but same diffusion coefficient. And while I run this, I want you to notice just how different the dynamics are. If you increase the screening length, it seems that there are a large number of defects active at any given time. Those are the bottom simulations. But those defects move much more slowly. But if the screening is very weak, there's very low screening, like on top, it's very hard for the plasma to form those defects. But when they do form, they're much quicker. And sort of these 2 effects, the average number of defects, the sort of activation energy to form a defect, and then the activation energy of defect migration, even though they're different and they scale differently, they come together to get you the same mean diffusion coefficient. My point is that the work is never finished. There's always another interesting thing to unpack. Why is the mean defect density dependent on the screening length? Why is the mobility dependent in this interesting way? And again, it's something that we will be cracking in the next year, but I think it's always important to end with open questions and forward-looking science. And so with that, I'm slightly past the 4:50 mark, and I think now would be a natural time to thank you all very much for your attention. Wish you good luck on your finals, and I hope you all have a very merry whatever it is you do once you're done with finals. Do we need a moderator for questions, or should I just pick hands? Excellent. And then when should I cut myself off? Right at 5? Are there any questions? In the interest of equity and inclusivity, I ask that the first question be from a student. Yes, hello, what's your name?
Nathan,
Hi, Nathan, I'm Matt. Nice to meet you. What's your question?
if you had a coefficient, where do you, are you solving fixed law, or are you kind of, what is the, I guess, the application?
What's the application? So diffusion is the microscopic input for the elastic modeling in neutron stars. So the neutron star crust is deformed by the magnetic field evolving. There's magnetic stresses. And we want to understand how the crust breaks, literally like an earthquake. So it's called a starquake. But this results in these like big magnetic outbursts from the star. So understanding the elastic properties, how a stressed crystal can relax diffusively through creep, if you're a materials person, is really the main application for why we're doing this sort of parameters. I saw another hand somewhere in the back. Yes, please.
So outside of the scenarios where you're purposefully causing sort of a lonely vacancy or lonely interstitial, do all interstitial and vacancy chains eventually form a very big loop, or do they sometimes just sort of like zoom off into the distance and never reconnect?
Yeah. That's a fantastic question. So I think this depends on the size of the volume. With the simulation sizes I have, they're guaranteed to eat their own tail, or if there's 2 pairs that form at the same time, they might link up in a weird figure-8 sort of way. In a realistic, effectively infinite medium, I don't necessarily think that's guaranteed. Because the Brownian motion in 3D, you go off to infinity rather than back to the start. The point is, I don't know, and it's sort of an open question, but interesting. Yeah, this is the chess game, right? Because you start from rules so simple, and then you get all material science from a purely repulsive potential. What? Yes, please.
What is the difference between this and like mundane solid objects? Are we just trying to recreate something plasma and analogous to solid?
Yeah, it's a solid, and we recover a lot of solid material science in these plasmas.
Yeah.
But my point is that these plasmas are physical. They do show up in neutron stars and white dwarfs. I just didn't want to bore you with astrophysics because I didn't think you would care. Yes, please.
Can you bring this down to dusty plasmas almost exactly?
I am so glad you asked, because there was another question in the middle of my talk asking me if there was data. And the answer is that the data that we can compare to comes exclusively from dusty plasmas. Take a dust, put an electric charge on it. The density is 1 trillion times lower than in a neutron star, but it's at room temperature, and then you can test this stuff. If you can confine a dusty plasma that's big enough, long enough, and track all the particles with lasers, which gets to be a technical challenge. Yes, please.
This might be more of a personal than a technical question,
That's fine.
but when you teased your 2025 fusion work, you said for reasons. You're doing a very particular kind of fusion for reasons. And then the next two slides, you go into this, I guess it looked like disarmament type of advocacy. Can you at least kind of like give some your thoughts on balancing those two?
Balancing. Can I ask you a personal question before I answer?
Yes.
What do you do and what are you going to be when you grow up? It's okay if you don't know.
Always something that's a good for it.
I see. So I want to understand your motivations for asking this question. There's something deeper that you might like to know.
Yes.
Yeah, so what?
Yes, what did I tell you?
Is this relevant to sort of your career choices in a way?
Maybe.
Okay, so tell you what, come talk to me afterward and we can have a great one-on-one about this.
Okay.
Great. I'm not deflecting. I just, this will be a one-on-one. This will be better if we can have a back and forth. I have time for like 2 more minutes of questions, right?
I'm sorry, that was me.
So it's great to see the universality of these laws. So we observe, as you said, we observe some of these statistical behaviors in semiconductors. Are these avalanche events at some point? These are the vacancies evolve like avalanches.
Okay, so the question was, do these vacancies evolve like avalanches?
Yeah.
So when you say an avalanche, you mean one vacancy
Triggers,
spawns more in
yeah.
its wake? I would love to know the answer to that, because I definitely have sort of a conceptual inkling that the presence of a defect lowers activation energies in its immediate surroundings, because it creates a little local bubble of disorder, which should lower activation energies for more defect formation. But I haven't quantified it, and I suspect there's very clever material scientists out there who have very strong opinions, but the answer is I don't know.
We are seeing similar behaviors in semiconductors that are triggered by avalanches. So yeah.
I will take one more question, and then I will let you all go free. Yes, please.
Perturb the system, does the perturbation progress like with the plasma frequency, or does it have some other,
What kind of perturbation are you asking about?
I don't know, if I displace a line of charge, I guess, kind of in like the usual teaching, teaching way you teach the plasma frequency, you have sort of a perturbation, how quickly does it respond to it? Does it stay the same, or does it have some other?
It's like a sound crossing timescale. Yeah, it's set by the potential and the sort of wells rather than. Yeah. All right, well, thank you all so much for coming. It's been a lot. And thank you to everyone on Zoom. I hope you had a nice time. I hope you had good sound quality.
Me too. Thank you. I'm sorry that went out in the middle. That's a really good presentation.
Thank you. People are still sticking around, but I'm gonna.
Well, there was something I was gonna ask you. Oh, have you ever watched like the Professor Dave explain